Hello student friends, hope you all are doing great. Welcome back to ChemMax channel. Today I am going to explain Ablok elements which are lanthanides and actinides and their general characteristics. Here I am going to give a general idea in a simple manner. In the periodic classification of elements, the elements have been broadly divided into four blocks, namely S, P, D block and F blocks. And this division is based on the type of atomic orbital which receives the last electron in the atom. Now we are going to know about the Ablok elements. The elements in which the last electron enters the f orbital of the atoms are called Ablok elements. Coming to their general electronic configuration, n-2f 1 to 14, n-1d 0 to 1, ns2. That means when the last electron is added to the third to the outermost energy shell, that is anti-penultimate shell, which is n-2f. And the last electron, when it is added to the next to the outermost electron, which is called penultimate shell, which is n-1d. These elements are also called as inner transition elements and consists of two series of elements, and they are placed at the bottom of the periodic table, and these two series are generated by the filling of characteristic electrons in the 4f orbitals and 5f orbitals. The series involving the filling of 4f orbitals following lanthanum is called Lanthanide series. The elements present in the series are called lanthanides. There are 14 elements in this series, and starting with the cerium, ending with the lutetium. That means after lanthanum, cerium to lutetium are called lanthanides, and these are also called as rare earth elements. Coming to the actinides, the series involving the filling of 5f orbitals is called actinide series, and this series follows actinium, and the elements present in this series are called actinoids. They include the elements from thorium to lawrencium. After actinium, thorium to lawrencium, these 14 elements are called actinides, and these are also called as 5F series. In the BSc level, they usually ask in the examination differences between lanthanides and actinides or similarities between lanthanides and actinides. Here I am going to try to explain the properties of lanthanides and actinides with the help of this table. First, coming to the similarities between lanthanides and actinides, the general similarities. In both the series, the predominant oxidation state is +3. That means the common oxidation state of both lanthanides and actinides are +3. In both the series, f orbitals are being progressively filled. Means like a 4f0, 4f1, 2, 3, 4 and etc. And both show decrease in covalent and ionic radii with increase in atomic number. This is also called as lanthanide contraction and actinide contraction. I think so you have heard about this term. Once again, the lanthanides and actinides show decrease in covalent and ionic radii with increase in atomic number, which is also called as lanthanide contraction and also actinide contraction. Elements of both series have low electronegativity and are very reactive. The nitrates, perchlorates and sulfates of the trivalent actinides as well as lanthanides are soluble, while the hydroxides, fluorides, carbonides are insoluble. Actinides also like lanthanides show ion exchange behavior. Here, the first property, oxidation states. All lanthanides exhibit a common stable oxidation state of +3. In addition this, some lanthanides show +2 and +4 oxidation states also in solution or in solid compounds. For example, cerium and terbium exhibit +4 oxidation states and they attain F0 and F7 configurations respectively. Europium and ytterbium get F7 and F14 configurations in +2 oxidation state. Whereas lanthanum, gadolinium and lutetium exhibit only +3 oxidation states. So, after losing 3 electrons or 2 electrons or 4 electrons, they acquire stable electronic configurations of empty, off-filled or completely filled 4f subshells. Actinides show different oxidation states such as +2, +3, +4, +5, +6 and +7. However, +3 oxidation state is most common and they have a wide range of oxidation states unlike lanthanides because the 5f, 60, 7s energy levels are of comparable energies. Therefore, all these three subshells can participate. Binding energies of 4f are higher whereas 5f are lower. And shielding effect, 4f electrons have greater shielding effect, therefore the contraction in their ionic radii is less. 5f electrons have poor shielding effect, therefore the contraction in their sizes is more. In the Lanthanide series, as we move from one element to another, the nuclear charge increases by 1 unit and 1 electron is added. The new electrons are added to the same inner 4f subshells. The 4f electrons shield, that means protect each other from the nuclear charge quite poorly because of the very diffused shapes of the f orbitals. The nuclear charge increases by 1 at each step. Hence, with increasing atomic number, nuclear charge and the effective nuclear charge experienced by each 4f electron increases. As a result, the whole of 4f electron shell contracts at each successive element. Though the decrease is very small, this results in gradual decrease in size of lanthanides with increase in atomic number. The sum of these successive reductions gives the total lanthanide contraction. So it will be happened same in case of actinides also. But the 4f electrons have greater shielding effect. Therefore, the contraction in their ionic radii is less. But 5f electrons have poor shielding effect. Therefore, the contraction in their sizes is more. The tendency to form complexes is less in case of lanthanides. And in case of actinides, they have greater tendency to form complexes. Lanthanide compounds are less basic and actinide compounds are more basic. Lanthanides do not form oxions and actinides they can form oxions such as UO2 plus, NPO2 plus, PuO2 plus and UO2 plus. Coming to the radioactivity, except promethium, all are non-radioactive elements. But actinides, all are radioactive elements. And the color of lanthanide ions arises due to absorption in visible region of the spectrum resulting FF transitions because they have partly filled orbitals. And actinide ions are generally colored. The color of actinide ions depends upon the number of 5f electrons. And the colors arise due to electronic transition between various energy states within the 5f subshell, that means FF transitions. The main reason behind the color property of lanthanides and actinides are FF transitions. Lanthanides are paramagnetic and their magnetic properties can be easily explained. Whereas actinides are also paramagnetic in nature, but their magnetic properties cannot be easily explained because the magnetic properties of actinides are higher than the theoretical predicted values. The reason behind the color property and magnetic property is unpaired electrons present in the 4f or 5f orbitals. I hope this video helps you somewhat in your preparation. Thank you for watching.